Our universe holds secrets that break its own rules. Out there in the dark, cosmic phenomena exist that, by every law of physics we know, should be impossible. These are space anomalies, the universe's own glitches in the matrix, and they are actively dismantling our understanding of reality. By the end of this journey, you will witness 35 of the most profound cosmic puzzles that defy every explanation. We will see a galaxy being pulled toward a hidden monster and hear a radio signal from the void that has never been repeated. These are not just curiosities. They are clues screaming that our maps of the cosmos are woefully incomplete. What cosmic truth are we on the verge of discovering? Our cosmic journey begins with a force so immense it is dragging us toward an unseen destiny. Picture the Milky Way, our home galaxy of hundreds of billions of stars, not as a static island but as a ship caught in a relentless current. This is the reality imposed by the first and perhaps most humbling anomaly known as the Great Attractor. It is a gravitational focal point of unimaginable power, located in the general direction of the constellations Centaurus and Hydra. Every galaxy in our local neighborhood, including our own, is being pulled toward this invisible point at speeds exceeding 1 million miles per hour. We are not floating aimlessly, we are falling. The central problem, the true source of the mystery, is that we cannot see what is pulling us. The Great Attractor lies directly behind the Milky Way's crowded, dusty central plane, a region astronomers poetically call the zone of avoidance. It is like trying to see a distant city while standing in the middle of a blinding fog bank. Our own galaxy's stars, gas, and dust form an impenetrable wall to traditional optical telescopes, hiding the truth in plain sight. So we must listen to the universe's whispers in other ways. By meticulously mapping the motions of thousands of galaxies, we can trace the flow of this cosmic river back to its source, confirming the pull exists even if the engine remains hidden. What could possibly exert such a force? The leading theory suggests it is not a single object, but a colossal concentration of mass, a supercluster of galaxies so vast it defies easy comprehension, all shrouded in the zone's dust. Some estimates suggest the mass needed is equivalent to tens of thousands of Milky Ways, yet even that staggering idea might be incomplete. The pull of the Great Attractor seems to be part of an even larger flow, hinting that it, too, may be moving towards something else, a deeper gravitational anchor in the cosmic web. Other speculations point to concentrations of dark matter, the universe's invisible scaffolding, clumped together in a way we have never directly observed. Or could it be something more exotic, a flaw in the fabric of space-time itself? For now, it remains a silhouette against the cosmic light, a reminder that the most powerful forces shaping our fate can be the ones we are utterly blind to. The Great Attractor is a force we feel but cannot see, a hidden mass pulling everything toward it. Yet the next cosmic anomaly presents the opposite problem, a terrifying emptiness we can see but cannot explain. It is known as the Boötes Void, or more chillingly, the Great Nothing. This is not a simple gap between stars. It is a spherical region of space approximately 330 million light-years across that is almost completely devoid of galaxies. To grasp that scale, if our own Milky Way were placed at the dead center of this void, and you looked up at the night sky with the most powerful telescopes available in the early 20th century, you would see almost nothing. No neighboring spirals, no distant elliptical smudges, just a profound, unbroken blackness. It would not be until the 1960s that our technology would be sensitive enough to detect the handful of lonely galaxies scattered in this unimaginable desert. This void is not a vacuum, as it contains some intergalactic gas and those few isolated galaxies, but its emptiness is staggering. In a region of space large enough to hold tens of thousands of galaxies like our own, astronomers have found only about 60. The cosmic web, the large-scale structure of the universe, is supposed to resemble a sponge or a network of filaments, with dense clusters of galaxies connected by threads and separated by modest bubbles. The Boötes void is not a bubble, it is a cavern, a hole in the fabric of the cosmos so vast it contradicts our models of how matter should be distributed following the Big Bang. Gravity should have pulled matter into a more or less even web-like structure, not left a gaping chasm of this magnitude. So what could have carved out such a nothingness? One theory suggests a cataclysmic chain reaction in the early universe, where the first generations of stars exploded as supernova with such ferocity that they literally blew all the surrounding gas and potential galaxy-forming material clear out of the region, creating a sterile bubble that expanded over eons. Another, far more speculative idea is that the void is the imprint of a collision with another universe in the multiverse, a bruise on our cosmos where the fundamental forces interacted and left behind a scar of emptiness. The most haunting possibility is that there is no exotic explanation, that it is simply a statistical fluke in the distribution of matter, a 1 in a billion chance that happened to occur. But that feels like a surrender to mystery. When we visualize the cosmic web, a vast, luminous network of galaxy clusters and filaments, the Boötes void appears as a perfect spherical patch of darkness, a blank spot on the map that warns us our understanding of the universe's structure is still only a rough sketch. What other impossible emptiness might be lurking in the deep field surveys of tomorrow? From a void of terrifying emptiness, we turn to a burst of impossible sound. On August 15, 1977, a radio telescope at Ohio State University known as the Big Ear was performing its routine scan of the cosmos. It was listening to the universe on a very specific frequency, 1420 megahertz. This is the natural emission frequency of neutral hydrogen, the most common element in the universe, and it is considered a prime channel for any civilization wanting to announce its presence. That night, the telescope's automated system recorded a signal so powerful and so perfect it defied all expectation. For 72 seconds, a narrowband radio burst, 30 times louder than the cosmic background noise, blazed into the receiver. It had the exact signature astronomers would predict for an artificial, interstellar transmission. When researcher Jerry Amon reviewed the computer printout days later, he circled the alphanumeric sequence representing the signal's incredible strength and in the margin simply wrote one word, "Wow." The exclamation point said it all. The WOW signal remains, to this day, the most compelling and enigmatic candidate for a potential extraterrestrial transmission ever detected. Its characteristics were textbook perfect. It was narrowband, meaning it occupied a very specific radio frequency, unlike the broad spectrum of natural cosmic noise. It appeared and then disappeared as the Earth's rotation swept the telescope's field of view across that patch of sky, exactly as a distant, fixed source would. And it originated from the direction of the constellation Sagittarius, near the center of our galaxy, a region dense with stars. Yet, in the decades since, despite countless dedicated searches using far more sensitive equipment, the signal has never been heard again. It was a single, brilliant shout into the cosmic silence, followed by an eternal, puzzling quiet. The debate over its origin is a fierce one. Could it have been a human-made signal, perhaps a secret military transmission or a signal from a passing satellite, reflected off a piece of space debris in an extraordinary coincidence? Possibly, but no known human technology at the time matched its precise profile. Could it have been an extremely rare but natural astrophysical event, a burst of energy from a comet or a star that we simply do not understand? Some have proposed this, but no natural phenomenon we know of produces such a clean, narrowband signal on the hydrogen line. This leaves the most thrilling and unsettling possibility that for 72 seconds in 1977, we accidentally eavesdropped on a beacon. A deliberate, powerful transmission from an intelligence we have not yet met, a hello that came and went before we could even think to reply. You can hear a representation of that signal now, a simple tone that carries the weight of the universe's greatest question. That sound is a ghost in the machine of science, a single data point that challenges our place in the cosmos and whispers that we might not be alone after all. The wow signal was a fleeting shout, a single note in the cosmic radio silence. But what if the universe itself is whispering a secret through the motion of everything within it? This leads us to the fourth anomaly, known as dark flow, a discovery so controversial it suggests our entire observable universe might be caught in a current from beyond the horizon of everything we know. Imagine not just our galaxy, but entire clusters of galaxies, thousands of them, each containing hundreds of galaxies like our own, all moving together in a coherent stream. They are not drifting randomly. They are all being pulled in the same specific direction at astonishing speeds exceeding 1 million miles per hour. This is not the local pull of the Great Attractor. This is something vaster, more fundamental, and deeply unsettling. Astronomers detected this ghostly motion by studying the afterglow of the Big Bang itself, the cosmic microwave background. This faint radiation fills all of space like a fossilized echo of creation's first light. As these gigantic galaxy clusters move at incredible speeds, they scatter the photons of this ancient light in a subtle, detectable way, an effect named for the scientists who predicted it, the kinetic Sunyaev-Zeldovich effect. By meticulously mapping this distortion across the sky, researchers saw the pattern. It was as if they had thrown a handful of leaves into a river and watched them all drift steadily downstream, revealing a flow invisible to the eye. The terrifying implication is the source of the current. The pull is so vast and coherent that its origin point cannot lie within our observable universe. Everything that we can possibly see, from the nearest star to the most distant quasar, exists within a cosmic sphere defined by the distance light has had time to travel since the Big Bang, about 13.8 billion years in every direction. Yet the dark flow suggests these galaxy clusters are being tugged by something from beyond that bubble, something from a region of space whose light has not had time to reach us and may never will. So what could possibly exert gravitational influence from outside our cosmic horizon? The theories venture into the realm of the profoundly speculative. One possibility is a colossal, imprinted structure from the universe's inflationary period, a wrinkle in space-time so vast it predates the Big Bang as we understand it, a cosmic fossil guiding the flow of matter. Another, even more mind-bending idea is that the pull is from a neighboring universe in a multiverse, a separate bubble of reality so unimaginably close yet eternally separate, whose gravity somehow leaks through the fabric of existence to tug on our own. This is not just an anomaly, it is a potential crack in the foundation of modern cosmology. If confirmed, dark flow implies that our universe is not isotropic, not the same in all directions on the largest scales, which is a cornerstone assumption of our models. It hints that the Big Bang may not have been the absolute beginning, but merely a phase transition in a larger, older metacosmos. The controversy rages because the signal is subtle and some analyses dispute it, but the possibility remains, a haunting suggestion that we are not just residents of a universe, but passengers on it, moving toward a destination we cannot see, pulled by a hand from the other side of reality. Dark flow suggests a pull from beyond our cosmic horizon, but our own galactic center hides structures of impossible violence. Rising from the heart of the Milky Way, two colossal orbs of searing energy stretch halfway to the edge of our galaxy. These are the Fermi bubbles, first unveiled in 2010 by data from the Fermi Gamma Ray Space Telescope. Picture our familiar spiral disk of stars, a flattened pinwheel of light. Now imagine two symmetrical lobes, one north and one south of that disk, ballooning outward for 25,000 light-years each. They form a perfect hourglass of pure gamma radiation, the most energetic form of light in the universe, towering over the entire galactic plane. This is not a gentle glow. It is the signature of a cataclysm, a pair of scars on the face of our home galaxy that we somehow never noticed until recently. Their discovery was a shock precisely because they are so enormous. How could something 50,000 light-years tall, emanating from our own backyard, remain hidden for so long? The answer lies in the energy they emit. Our eyes and ordinary telescopes see only visible light, but the Fermi bubbles scream in gamma rays, invisible to human sight and blocked by our atmosphere. It took an orbital observatory designed to see the universe in this violent light to finally reveal these titanic structures. A composite image overlaying the gamma-ray data onto the familiar band of the Milky Way is breathtaking and humbling. It shows our galaxy not as a serene island, but as a cosmic engine with two blazing exhaust plumes. So what event could possibly forge such structures? The bubbles originate from the region of Sagittarius, a star, the supermassive black hole slumbering at our galaxy's core. The leading theory is that this black hole was not always so quiet. Sometime in the past few million years, it may have awakened in a spectacular feast, devouring an enormous cloud of gas or even a star. The resulting eruption would have blasted twin jets of relativistic particles, moving at nearly the speed of light, straight up and down out of the galactic disk. These jets would have inflated the bubbles, energizing the gas within to emit the gamma rays we see today. It would have been a brief, apocalyptic roar in the life of the galaxy. Another possibility points not to the black hole, but to a frenzy of star formation. If hundreds of massive stars were born simultaneously in the crowded galactic center, their combined stellar winds and subsequent supernova explosions could have created a powerful, spherical shockwave that inflated the bubbles. Yet both explanations strain under the sheer scale and perfect symmetry of the structures. The energy required is staggering, equivalent to perhaps 100,000 supernova exploding in concert. The event, whatever it was, must have been a singular, catastrophic outburst that briefly outshone the entire galaxy. The Fermi bubbles stand as a monument to a violent chapter in our galaxy's history that we missed, a reminder that even our cosmic home has secrets written in invisible, high-energy light. What other ancient eruptions might have shaped the Milky Way, leaving ghosts in wavelengths we are only now learning to see? The Fermi bubbles are a monument to chaotic, explosive power, but some cosmic structures display an eerie, almost artificial precision. Suspended in the constellation Monoceros, a celestial artist seems to have drafted a perfect geometric form against the dark canvas of space. This is the Red Rectangle Nebula, a stunning and profoundly puzzling object centered on the dying star HD 44179. Through the lens of the Hubble Space Telescope, it does not resemble the billowing, chaotic clouds of a typical planetary nebula. Instead, it presents a stark, symmetrical X-shape, its arms connected by concentric, ladder-like rungs of glowing gas that form a series of near-perfect rectangles. It looks less like a natural astronomical event and more like a cosmic blueprint, a piece of divine architecture or a beacon deliberately constructed. Such razor-sharp geometry defies everything we understand about the final stages of a star's life. When a sun-like star exhausts its nuclear fuel, it sheds its outer layers in a series of messy, often spherical eruptions. The resulting nebula should be a glowing, expanding bubble of gas, beautifully irregular like the Ring Nebula or the Helix Nebula. The red rectangle obeys no such rule. Its form suggests forces at work that are far more controlled and directional than a simple stellar sigh. So what cosmic loom could weave such a pattern? The leading theory involves not one, but two stars locked in a tight dance at the nebula's heart. This binary system is thought to be the engine. As the primary star began to die, puffing out its atmosphere, the intense gravitational influence of its companion star could have funneled that expelled material into two opposing cones or jets. If those jets were wobbling or precessing like a spinning top slowly tracing a circle, they could paint the intricate X shape across the sky over thousands of years. The remarkable rectangular rungs might then be explained by periodic puffs of material ejected at regular intervals, creating shock waves that light up as they expand into the older, slower-moving gas, like rings in a pond from repeated drops of water. The rich red color comes not from hydrogen, but from a rare type of carbon-based molecule known as polycyclic aromatic hydrocarbons, essentially complex soot fluorescing under the star's intense ultraviolet light. Yet, while the binary star model provides a framework, no computer simulation has yet perfectly recreated the nebula's stunningly crisp geometric perfection. The shapes are too clean, the symmetry too exact. It forces us to question whether we fully comprehend all the complex interactions between stellar winds, magnetic fields, and dust dynamics in these final dramatic acts. The red rectangle is not just a dying star. It is a masterpiece of cosmic physics, a sculpture carved by processes we are only beginning to map, reminding us that even in death, the universe can produce works of unnatural, breathtaking order. Geometry in the red rectangle nebula feels almost designed, a cosmic artifact of perfect symmetry. Yet another star presents the opposite, a pattern of chaos so bizarre it forced scientists to openly consider an artificial cause. This is Tabby's star, officially catalogued as KIC 8462852, a seemingly ordinary star over 1,000 light-years away in the constellation Cygnus. It behaves like nothing else in the galaxy. The story begins with the Kepler Space Telescope, a mission designed to hunt for planets by staring at stars and waiting for the tiny, periodic dips in brightness caused by a world passing in front. For most stars, Kepler found a gentle, rhythmic blinking. For Tabby's star, it found madness. The data revealed not tidy, repeating dips, but a series of deep, erratic, and asymmetrical dimming events. The star's light would plummet by staggering amounts, up to 22%, and then partially recover in jagged, unpredictable steps. These were not the 1% dips of a Jupiter-sized planet. This was as if something enormous and jagged, with no regular orbit, was repeatedly drifting in front of the star, blocking its light in a chaotic dance. The strangest event, dubbed Dyson Dip, saw the star's brightness drop gradually by over 20% and stayed dimmed for nearly a week. The light curves, the graphs of brightness over time, looked less like astronomy and more like a malfunctioning sensor. They were aperiodic, messy, and profoundly unnatural by any standard celestial mechanics. The immediate, thrillingly wild theory was that we were witnessing a megastructure. Specifically, a Dyson swarm, a vast collection of energy collecting panels or habitats orbiting the star, constructed by an advanced civilization to harness its total power. The irregular dips could be explained by a partially completed swarm, with huge clusters of collectors passing in front of the star at different intervals, their uneven shapes creating the jagged light curve. It was a hypothesis born of sheer desperation to explain the data, and for a moment it held the world's attention. Science, however, demands natural explanations first. Astronomers scrambled to find one. A giant swarm of comets, perhaps thousands of them, kicked into the inner system by a passing star, could create dust clouds that dim the light. But the scale required is immense, and such an event would be extraordinarily rare. Another idea involved circumstellar dust, a thick, clumpy ring of debris orbiting the star. Yet the dust should radiate infrared heat, and observations showed a puzzling lack of excess infrared radiation. A shattered planet, pulverized by a catastrophic collision, could create a vast, irregular field of debris. But the timing and persistence of the dimming events make even this dramatic scenario hard to fit perfectly. Each natural explanation has a flaw, a piece of the puzzle that does not quite snap into place. This is why Tabby's star remains a landmark case. It exemplifies the scientific process confronting the truly unknown. the star has been placed under intense, continuous scrutiny by telescopes around the world and in space, including Hubble and the Los Cumbres Observatory Network. Every new dimming event is captured, analyzed, and compared to models. The mystery has deepened further as long-term studies show the star has also been undergoing a very slow, secular dimming over the past century, fading by a significant fraction. Is it surrounded by a vast, dusty disk we cannot quite see? Is it undergoing internal stellar processes we do not yet understand? Or is it, against all odds, the first hint of intelligence on a scale we can barely comprehend? The light curve graphs of Tabby's star are more than data. They are a question mark written in photons, a persistent anomaly that refuses to be solved, reminding us that sometimes the most ordinary-looking point of light can hold the most extraordinary secret. Tabby's star forces us to question what might orbit a sun, but another discovery challenges the very foundation of what holds a galaxy together. There is a galaxy that should not exist, a ghostly smudge of stars called NGC 1052DF2. This ultra-diffuse galaxy is so wispy you can see right through it to the galaxies beyond, like a cosmic apparition. Its stars are spread so thin it contains only about 1/200th the mass of the Milky Way. But its true impossibility lies in what it lacks. According to every modern model of cosmology, dark matter is the invisible skeleton of the universe. This mysterious substance, which does not emit or reflect light, is believed to form vast halos around every galaxy. Its gravitational grip is what prevents galaxies from flying apart as they spin. Without this dark matter anchor, a galaxy's own stars should be flung into the void. Yet NGC 1052DF2 appears to have almost none. The evidence came from measuring the motions of its globular clusters, bright, dense balls of stars that orbit the galaxy's core. By clocking their speeds, astronomers can calculate the total mass pulling on them. The result was shocking. The clusters were moving slowly, lazily, as if there was almost no gravitational glue holding the galaxy together. The mass they measured matched almost perfectly the mass of the visible stars alone. There was no extra hidden mass, no signature of a dark matter halo. It was like watching a spinning carnival ride operate without a central axle, the cars moving in a slow, impossible orbit that defied physics. This discovery sent a tremor through astronomy. If dark matter is essential for galaxy formation, how did this one form without it? One possibility is that it is a tragic outlier. Perhaps it was born within a massive cluster of galaxies, and violent gravitational interactions with its neighbors ripped away its dark matter halo long ago, leaving behind a skeleton of stars. Another, more radical idea is that our theories of gravity itself are wrong on galactic scales. Modified Newtonian dynamics, or MUND, proposes that gravity behaves differently when it becomes extremely weak, eliminating the need for dark matter altogether. In a MUND universe, a galaxy like DF2 might be rare but not impossible. Yet DF2 is not alone. A handful of other similar dark matter-deficient galaxies have since been found, suggesting this might be a new class of object, not just a fluke. When you compare an image of this ethereal galaxy to a simulation of a typical galaxy embedded in its glowing halo of dark matter, the contrast is stark. One is a faint, lonely gathering of stars. The other is a brilliant knot of light at the heart of a massive, invisible sphere of gravitational influence. DF2 forces a brutal choice. Either our understanding of how galaxies are born and survive is critically incomplete, missing a process that can build a galaxy from stars alone, or the dark matter paradigm, the cornerstone of modern cosmology, has a fatal flaw. This ghostly galaxy is not just an oddity. It is a direct challenge written in starlight to the rules we thought governed the cosmos. A galaxy without dark matter defies the rules of cosmic structure, but some anomalies are so new we do not even have rules for them yet. In 2019, astronomers mapping the sky in radio waves stumbled upon something utterly bewildering. circles of ghostly light so vast and faint they had been missed by every other telescope in every other wavelength. They named them odd radio circles, or ORCS. These are not planets, nebulae, or galaxies. They are colossal, perfectly circular rings of radio emission, hundreds of thousands of light years across, floating in the deep field like cosmic smoke rings. To grasp their scale, a single ORC could easily envelop an entire galaxy like our Milky Way with room to spare. Yet if you point the world's most powerful optical, infrared, or X-ray telescopes at the exact same spot in the sky, you see nothing. Absolutely nothing. They are phantoms visible only in the specific, long wavelength light of radio. This makes them profoundly strange. In astronomy, most objects emit some radiation across multiple parts of the spectrum. A star glows in visible light and infrared. A supernova remnant shines in X-rays and radio, but an object that is radiant only in radio and on such a stupendous scale is unprecedented. It is as if you walked into a silent, pitch-black room and felt a powerful, warm breeze coming from a source you cannot see or hear. The Discovery images from radio telescope arrays like a SKP in Australia show these perfect, ethereal rings, often with a brighter edge, like bubbles frozen in the act of expansion. They are not artifacts or errors, they are real structures, and we have no idea what made them. The hypotheses scientists have proposed are as wild as the objects themselves. One leading idea is that they are the titanic shockwaves from a catastrophic event that occurred at the center of a galaxy, perhaps the merger of two supermassive black holes. Such an event could send a spherical tsunami of energy blasting outwards for millions of years, lighting up a shell of intergalactic gas that we see as a ring. Another, more speculative theory suggests they could be the throats of wormholes, theoretical tunnels in space-time, though this is considered far less likely. A third possibility is that they are the aftermath of a gargantuan stellar explosion, a hypernova on a scale we have never witnessed, whose blast wave traveled for eons before finally lighting up a spherical shell of material. Or perhaps they are something else entirely, a previously unknown phase in the life cycle of galaxies, or an interaction with the intergalactic medium we have never before detected. The most humbling fact is that ORCS represent a completely new class of astronomical object. They were not predicted. They were not even on our list of things to look for. They simply appeared in the data, a reminder that our maps of the universe are still so incomplete that we can still find entirely new categories of things that are bigger than galaxies. They are cosmic signposts pointing to a whole new chapter of physics, written in a language of radio waves we are only just beginning to translate. The radio ghosts of odd radio circles hint at unseen forces, but in 2017, a visitor from another star system arrived in our own cosmic backyard. This was Oumuamua, the first confirmed interstellar object ever detected passing through our solar system. Its Hawaiian name means scout or messenger from the distant past, and it lived up to that title by delivering a profound mystery. Discovered by the Pan-STARRS telescope in Hawaii as a faint point of light already speeding away from the sun, Oumuamua was immediately strange. Its path was hyperbolic, meaning it was not bound by the sun's gravity and was just passing through on a one-way trip from the depths of the galaxy. As astronomers scrambled to observe it, the oddities multiplied. First was its shape. By measuring how its brightness changed dramatically as it tumbled, scientists deduced it was highly elongated, perhaps 10 times as long as it was wide. Imagine a cosmic pancake or a cigar tumbling end over end through the void, a shape unlike any asteroid or comet we see in our own system. Second was its motion. As it rounded the sun and headed back out to interstellar space, it did something inexplicable. It sped up. This non-gravitational acceleration was subtle but undeniable. Comets do this when sunlight vaporizes their icy surfaces, creating a jet of gas that acts like a weak rocket engine. but Oumuamua showed no visible coma, the fuzzy cloud of gas and dust, and no tail. It was dark, reddish, and appeared completely inert to our telescopes. It was accelerating with no visible exhaust. This single fact ignited a firestorm of debate. The scientific community rallied to find natural explanations. Could it be a hydrogen iceberg? Such an object, born in the cold core of a giant molecular cloud, would sublimate in sunlight, giving a push without leaving a dusty trail. But hydrogen ice is fragile, and it is unclear if it could survive a long interstellar journey. Another idea proposed it was a fragment of a Pluto-like world made of solid nitrogen. As nitrogen ice vaporized, it could provide the thrust. Yet both theories felt like forcing a square peg into a round hole, requiring very specific and rare conditions. The absence of a clear answer opened the door to a more speculative, thrilling possibility. Could Oumuamua be artificial? The most famous proponent of this idea, Harvard astronomer Avi Loeb, suggested it might be a piece of discarded light sail technology. A light sail is a thin, reflective sheet pushed by the pressure of sunlight itself. A large, thin sheet of material, perhaps broken from a larger craft, could explain the unusual shape and the sunlight-powered acceleration without any visible outgassing. It would be space junk from an alien civilization, a derelict piece of machinery sailing the galactic currents. Artist concepts capture this haunting ambiguity. They show a dark, reddish, elongated object tumbling silently against a starfield, a simple shape that could be a weird rock or a fragment of a long-dead probe. The truth is we will never know for certain. Oumuamua is now far beyond the reach of our telescopes, a fleeting enigma that visited for mere weeks. Its brief passage forced us to confront a humbling reality. After millennia of looking up, when an object from another star finally came calling, we were not prepared to understand it. It left behind a single, tantalizing data set and a galaxy of questions, proving the universe's messengers often speak in riddles we are only beginning to hear. Oumuamua was a fleeting messenger from the stars, but our universe's oldest light holds a permanent, chilling scar. Embedded in the cosmic microwave background, the faint afterglow of the Big Bang itself, lies a region so profoundly cold it should not exist. Known simply as the cold spot, this anomaly is not a small blemish. It is a colossal patch of sky over 1 billion light-years across, where the temperature of the primordial radiation is a tiny but significant fraction lower than the surrounding average. This is not a measurement error. Multiple independent satellite missions from Oumuamua to Planck have confirmed its presence. It stares back at us from full sky maps of the CMB, a vast circular bruise of blue and purple against the warmer reds and yellows, a splash of cosmic chill in the first light of creation. In a universe that is supposed to be broadly uniform on the largest scales, such a gigantic, specific cold region is a deep violation of expectation. Standard inflationary cosmology, our leading theory for the universe's explosive first moments, predicts that the CMB should have only very small, random fluctuations in temperature. The cold spot is not just a fluctuation. It is a monumental outlier, a statistical anomaly so extreme that some calculations suggest the odds of it occurring by random chance are less than 1 in 100,000. It is a feature in the foundation of reality that our best models cannot easily build. So what could have left such a mark? One of the more conventional, yet still extreme, explanations points to a supervoid. The theory is elegant in its simplicity. If there exists an enormous, underdense region of space, a void on a scale dwarfing even the Boötes void between us and the surface where the CMB was emitted, light passing through it would lose energy. This is due to the integrated Sachs-Wolf effect. As photons climb out of a vast gravitational well, or in this case, climb into one and then out of a void, they redshift, appearing cooler to us. The problem is one of scale. To produce the observed cold spot, this void would need to be unimaginably large, perhaps over 2 billion light-years wide and incredibly empty. While astronomers have searched for such a structure, the observed cosmic web simply does not contain voids of sufficient magnitude. The voids we find are big, but not nearly big enough to explain the chill. This failure of the simplest natural explanation opens the door to something far wilder. Could the cold spot be the imprint of a collision with another universe? This idea emerges from theories of eternal inflation and the multiverse. In this scenario, our universe is one bubble in a frothing, infinite meta-cosmos. During its early inflation, our bubble might have brushed against a neighboring one. The energy released at that boundary, a cosmic bruise, could have left a permanent, cooler imprint on our CMB. It would be a fossil of a contact with a reality forever separate from our own, a scar from a battle between different sets of physical laws. The image is staggering. A map of the universe's first light, a baby picture of existence, might contain a shadow not of something within our cosmos, but of the cosmos next door. While this multiverse collision theory is highly speculative and currently untestable in a traditional sense, its very plausibility highlights the depth of the mystery. The cold spot forces a profound choice. Do we accept that we live in a universe capable of producing such a statistically unlikely feature by sheer random chance? Or do we take it as evidence that our universe is not alone, and that its very fabric bears the marks of a larger, more complex reality? This cold patch on the sky is more than a data point. It is a whisper from the moment of Genesis, a message in the cold that either speaks of a monstrous emptiness within, or a shocking contact with a world beyond. The cold spot is a fossil from the universe's first light, but the newest window into the cosmos is revealing galaxies that should be infants, yet look like adults. The James Webb Space Telescope, our most powerful time machine, has peered deeper into the past than ever before, capturing light that has traveled for over 13 billion years. What it found there has sent a shockwave through cosmology, revealing galaxies in the cosmic dawn that are not just bright but impossibly mature. Galaxies like GLSSZ 13, glimpsed a mere 300 million years after the Big Bang, are not the faint, chaotic blobs of primordial gas we expected. They are massive, structured, and appear fully formed, with disks and bulges that should have taken billions of years to assemble. In the standard model of cosmology, the universe began in a hot, dense state, and then structure grew slowly and gradually. Tiny quantum fluctuations were amplified by gravity over eons, first pulling together dark matter halos, which then attracted gas to form the first stars, which then clustered into the first small, irregular galaxies. This process should have been messy and slow. The James Webb images tell a different story. Its deep field views, like the one of the galaxy cluster SMACS 0723, are not just beautiful. They are revolutionary. Within them, points of light from the earliest epochs are not faint smudges. They are bright, distinct, and numerous. These galaxies are too big, too bright, and too evolved for their age. It is as if archaeologists digging in a layer of earth from the Stone Age uncovered a fully formed modern city complete with steel skyscrapers. The implications are staggering. This anomaly is not a single odd object, but a population of them, a pattern that breaks the model. Scientists call it a cosmic breaker. If these observations hold, it means our timeline is wrong, our understanding of galaxy formation is incomplete, or our physics is missing a crucial piece. One possibility is that dark matter in the early universe was somehow different, perhaps warmer or more interactive, allowing structures to collapse and form stars with terrifying efficiency. Another is that the first stars were not like the stars we know, but monstrously large and bright, forging galaxies in a frenzy. The most radical idea is that we need to revise the age of the universe itself, or consider that the Big Bang was not the absolute beginning, but a transition from a prior state. The stunning James Webb Deep Field images, with their tapestry of thousands of galaxies, are now a puzzle. Each of those tiny, red-shifted dots from the farthest edges is a question. How did they get so organized so quickly? The light we are seeing is a baby picture, but the babies in the photo look like grown-ups. This forces a profound and exciting reckoning. We may be witnessing the first evidence that the story of our cosmos, from its fiery birth to the present day, needs a dramatic rewrite. A cosmic engine has broken free from its galaxy and is now carving a river of light across the void. This is the runaway supermassive black hole, an object with a mass of 20 million suns caught in the act of a breathtaking escape. Hubble's Space Telescope images revealed not the black hole itself, but its brilliant, unintended signature, a contrail of newborn stars stretching 200,000 light-years long, twice the diameter of our Milky Way. It is a blazing highway of stellar nurseries, a line of fire painted across intergalactic space where there should be only darkness. The black hole is moving so fast it could travel from Earth to the Moon in just 14 minutes. At that velocity, it is not merely drifting, it has been catapulted. The leading explanation is a celestial game of gravitational billiards of almost unimaginable violence. The scene begins with 3 galaxies, each with its own central supermassive black hole, drawn together in a slow, cosmic dance. As the galaxies merge, their black holes begin to orbit one another, tightening their spiral. In a rare and precise configuration, 2 of them can form a tight binary system. When the third approaches, the complex gravitational interplay can slingshot one of the black holes outward at phenomenal speed, like a stone from a sling, while the binary pair recoils in the opposite direction. The ejected monster is not traveling alone. As it plows through the dense gas surrounding its former galactic home at supersonic speeds, it shocks and compresses that material. The gas cools, collapses, and ignites into a chain of new stars directly behind the black hole's path. What we see is not a trail of stars being pulled along, but a wake of creation left behind. The proposed animation of this event is both beautiful and terrifying. It would show 3 glowing galaxies intertwining, their cores brightening as the black holes duel. Then, a single point of immense gravity is flung from the chaos, screaming across the screen. In its wake, a narrow, brilliant line of blue-white star clusters sparks to life, a cosmic jet trail marking its passage through the intergalactic medium. The sheer energy required for this slingshot is staggering, making such events exceptionally rare. This observation forces us to rewrite the life story of galaxies and the monsters at their hearts. We assumed supermassive black holes were forever anchored to the galactic core, the unmoving anchors around which everything else revolved. This proves they can be evicted, sent wandering through the cosmic wilderness as rogue giants. What happens to a galaxy that loses its central black hole? Does it slowly unravel, or does it birth a new one from the remaining gas and stars? And what becomes of the runaway itself? It will travel forever in the emptiness between galaxies, a dark king without a kingdom, its brilliant star trail eventually fading to cold red embers. This single streak of light is more than a curiosity. It is direct evidence that the universe can play a game of gravitational darts with the most massive objects in existence, and that from catastrophic chaos it can draw a line of newborn suns. A runaway black hole leaves a trail of creation, but some stars suggest a more deliberate kind of engineering. Among the millions of stars catalogued by our telescopes, a handful stand out not for what they are, but for what they might be hiding. These are the Dyson Sphere candidates, stars whose light tells a story of possible artificiality. The most famous is TYC 6111-1162-1, a star whose strange behavior was flagged by citizen scientists in the Planet Hunters project. Its light curve shows deep, irregular dips reminiscent of Tabby's star, but with an even more peculiar signature. When astronomers looked at it in infrared light, they found a significant excess of heat. This combination is the key clue. The concept comes from the physicist Freeman Dyson, who speculated that a civilization advanced enough to need vast amounts of energy might eventually build a swarm of orbiting collectors to completely enclose its star, capturing nearly all of its light output. This is a Kardashev Type II civilization, one that commands the power of an entire star system. We would not see the visible light from the star itself, but according to the laws of thermodynamics, all that captured energy must go somewhere. It would be used and eventually re-radiated as waste heat, a telltale glow in the mid-infrared part of the spectrum. So the search is not for a shiny, solid shell, but for an object that is oddly dark in visible light, yet inexplicably bright in infrared. TYC6111-1162-1 fits part of this profile, showing those strange dimmings alongside infrared excess. The critical scientific work is in the ruling out. Could this simply be a natural dust cloud, perhaps from a catastrophic planetary collision or a huge swarm of comets? Absolutely. In fact, natural explanations are always the first and most likely answer. The irregular dimming could be caused by circumstellar debris, and the infrared excess could be from that same dust warming up. The hunt for Dyson spheres is therefore a process of elimination, searching for an object where all natural explanations fall short. It is a branch of SETI, the search for extraterrestrial intelligence, that looks not for radio signals, but for the archaeological footprints of cosmic-scale engineering. A speculative visualization of such a project is breathtaking. It would not be a perfect, solid ball, but a vast, rotating swarm of individual panels or habitats in independent orbits, a complex latticework that partially obscures the star. From a distance, the star would flicker erratically as these collectors pass in front of it, and the entire system would glow with a dull, warm infrared light. Finding even a single, unambiguous candidate would be the most profound discovery in human history, proof that we are not the only builders in the universe. For now, stars like TYC6111-1162-1 remain intriguing mysteries, reminders that as we sift through the data of the cosmos, we must keep our minds open to the possibility that the greatest anomalies are not failures of nature, but the signatures of intelligence. The search for cosmic-scale engineering looks for intelligence in the present, but to understand our origins, we must recreate the first moments of existence. Deep beneath the border of France and Switzerland, the world's most powerful machine is doing exactly that. The Large Hadron Collider at CERN smashes lead nuclei together at velocities approaching the speed of light, recreating for a fleeting instant a state of matter not seen since the universe was less than a microsecond old. This is the quark-gluon plasma, a primordial soup where the fundamental building blocks of protons and neutrons, quarks and gluons, roamed freely in a seething, perfect liquid. Within the debris of these unimaginably violent collisions, physicists have now found something startling: particles that simply do not belong in our modern world. They are called X-particles, and their very existence is a direct window into the chaotic infancy of everything. These are not the ordinary protons and neutrons made of three quarks that form the atoms in our bodies. X-particles are exotic, composite states held together by the strong nuclear force, often containing 4 quarks, a configuration known as a tetraquark, or even 5 quarks, a pentaquark. In today's cold, sparse universe, these complex arrangements are incredibly rare and unstable, falling apart almost instantly. But in the extreme density and temperature of the quark-gluon plasma, they could form naturally and abundantly, like complex crystals forming in a superheated solution. The data from the detectors is a storm of information. Visualizations show the aftermath of a collision as a spherical explosion of particle tracks, a tangled web of lines curving in magnetic fields, each representing a daughter particle from the shattered nuclei. Sifting through billions of these events using advanced machine learning algorithms, the CERN collaboration identified the subtle decay signatures of these elusive X-particles, proving they were forged in the miniature Big Bangs created in the collider. Their significance is profound. These particles are not just curiosities, they are fossils from the first microseconds, carrying information about how quarks and gluons behaved when the universe was 1 trillion degrees hot. By studying their properties and how often they form, physicists can test the fundamental theory of the strong force, quantum chromodynamics, under conditions we can never observe in the sky. They help us understand the transition, that critical moment when the universe cooled enough for quarks to lock together into the protons and neutrons that would later build atoms, stars, and planets. This leads to the central mystery: why did these X-particles seem to vanish? As the universe expanded and cooled at an incredible rate, the quark-gluon plasma condensed. The environment that allowed these exotic multi-quark states to form and persist simply disappeared. The 3 quark arrangements of protons and neutrons became the stable, preferred configuration in a colder, less energetic cosmos. The X-particles faded from existence, their brief reign over almost before it began. Finding them now is like discovering a unique type of ice crystal that only forms at a specific, extreme pressure and temperature that no longer exists naturally on Earth. By recreating those conditions in a lab, we proved they were once real, and we learned the rules that govern the universe's first and most dramatic phase change. These particles are ghosts from a time before time had meaning, and their discovery tells us that the recipe for our reality was written in a searing, exotic alphabet we are only now beginning to decipher. The collisions at CERN recreate a universe of pure chaos, but out in the cosmos, we find a different kind of physics-defying phenomenon: perfect order. Around our neighboring galaxy, Andromeda, something is moving with an eerie, synchronized grace. Its collection of small satellite galaxies, which should be orbiting in a chaotic, scattered swarm, are instead arranged in a vast, thin disk. They are like flies caught on a giant, invisible phonograph record, all circling the central galaxy together in a single, coherent plane. This is not unique to Andromeda. We see similar, flattened arrangements around our own Milky Way and other large galaxies. It is a pattern so consistent and so wrong that astronomers have given it a name: the disk of satellites problem. According to our best cosmological simulations, which include the gravitational pull of dark matter, satellite galaxies should be falling into the larger galaxies' grasp from all directions. They are the leftover scraps from the chaotic process of galaxy formation, captured over billions of years. Their orbits should be random, tilted at all angles, creating a spherical cloud of satellites around the host. The simulations show exactly that: a buzzing, three-dimensional hive of motion. The reality we observe is starkly different. Observations, particularly deep surveys of Andromeda's satellite system, reveal that a significant majority of these small galaxies share the same orbital plane. They are not scattered, they are aligned. A diagram of Andromeda makes this stunningly clear. You see the grand spiral of the main galaxy, and around it not a sphere of dots, but a distinct, flattened ring of its companion galaxies, all tracing paths within the same narrow slice of space. This presents a profound dilemma for the standard model of cosmology. Dark matter halos are thought to be roughly spherical, and they should pull in satellites from random directions as the galaxy assembles. Getting so many satellites to agree on a single plane of rotation is like throwing a handful of marbles into a bowl and watching them all spontaneously start rolling in perfect concentric circles. It should not happen by chance, so what force could be choreographing this cosmic dance? One line of thought suggests that the satellites did not fall in independently, but were born together. Perhaps they formed from a single, massive filament of gas and dark matter, a cosmic river that fed the growth of the central galaxy. All the satellites condensing from that long, thin structure would naturally inherit its flattened geometry, like beads strung on a wire that then begins to rotate. This implies that dark matter itself might have a more intricate filamentary substructure than our simple halo models assume. Another, more radical idea challenges the dark matter paradigm itself. Theories like modified Newtonian dynamics, or MND, which modify the laws of gravity on large scales, can sometimes produce flattened satellite planes more naturally because the gravitational forces in such a framework have a directional preference. Yet even these alternatives struggle to explain the exact thinness and coherence we see. The synchronized rotation stands as a quiet, persistent rebuke to our simulations. It tells us that the story of how galaxies gather their families is missing a crucial page, one that might involve the memory of their birth within the cosmic web or a new understanding of the invisible forces that bind them. This is not a violent anomaly, but a graceful one, a whisper of order in a universe we thought was built on chaos. A graceful plane of satellites hints at a forgotten order, but a single, ancient star stands as a lonely monument to a broken rule. In the sparse halo of our Milky Way, astronomers have found a star that simply should not be. Catalogued as SDSSJ 102915+172927, this faint, elderly sun is a time capsule from the universe's first few 100 million years. Its composition is shockingly pure. It is made almost entirely of hydrogen and helium, the primordial elements forged in the Big Bang itself. The metals, what astronomers call any element heavier than helium, are nearly absent. Their abundance is hundreds of times lower than in our own sun. This makes it one of the most chemically pristine stars ever discovered, a living relic from the cosmic dawn. Yet its very existence defies our story of how the first stars were born. According to our most trusted models, the very first generation of stars, called Population 3, were behemoths. They formed from clouds of pure hydrogen and helium, without heavier elements like carbon and oxygen to help the gas clouds cool and fragment through radiation. These clouds could not collapse into small, stable stars. Instead, they had to collapse into monstrous giants, hundreds of times the mass of our sun, that lived fast, died young, and exploded in titanic supernova that seeded the universe with its first metals. This is the established cycle: no metals, no small stars. Then we found SDSSJ 102915+172927. It is a small, long-lived star with almost no metals. It is a paradox. A spectrum of this star tells the story visually. Where a normal star's spectrum would be crossed by numerous dark absorption lines from elements like iron, calcium, and sodium, this star's spectrum is hauntingly clean. The hydrogen and helium lines are stark and dominant, but the metal lines are so faint they are almost invisible against the background. It is a chemical fingerprint showing a universe before pollution, a star that somehow formed without the crucial ingredients we thought were necessary for its birth. So how did this impossible star come to be? One theory suggests it might be a second-generation star, born from the ashes of a very peculiar first supernova. Perhaps that first massive star died in a faint, asymmetric explosion that ejected mostly its outer layers of hydrogen and helium, locking the newly forged metals into a collapsing black hole at the core. The next generation of stars that formed from this selectively enriched gas would then be metal-poor, but not zero metal. Another, more radical idea is that our understanding of cloud physics in the early universe is incomplete. Maybe turbulent flows or different cooling pathways allowed a few small, stable knots to form in those primordial clouds without needing metals as a coolant. This star is a single data point screaming that our picture of the first chapters of star formation is missing a crucial page. It is not just an old star. It is a survivor from an era before the rules were set, a quiet witness to a process we thought was impossible, proving that the infant universe found a way to create fragile suns in the pure, silent dark. That ancient, metal-poor star whispers of a universe that broke its own rules at the very beginning, but another ghostly galaxy presents a modern, direct challenge to the cosmos's invisible foundations. This is a GC114905, an ultra-diffuse galaxy so transparent it is almost a cosmic mirage, and it has become a second, powerful witness in the case against our understanding of dark matter. Following the earlier discovery of the dark matter-deficient galaxy NGC 1052DF2, astronomers hoped it was a bizarre fluke, a cosmic accident. Finding another one, however, changes everything. It transforms an oddity into a pattern, a single strange note into a troubling new melody. A GC114905 was studied with immense care using the Very Large Array of Radio telescopes. The goal was to map the rotation of its sparse, swirling gas by measuring the subtle Doppler shifts in the radio waves it emits. The resulting data plot is stark and revealing. On one axis, you have the distance from the galaxy's center. On the other, the orbital speed of the gas. In a normal spiral galaxy like our Milky Way, this plot shows a steep rise and then a flat line. The gas on the outer edges moves just as fast as the gas near the core, a phenomenon that can only be explained by the gravitational grip of a massive, unseen dark matter halo. Now look at the plot for a GC114905. The line does not stay flat, it falls. The rotational speed of the gas drops steadily as you move outward from the center, exactly as you would expect if only the visible mass of the stars and gas were pulling on it. There is no extra, hidden mass keeping the outer reaches whipping around at high speed. The galaxy is, for all intents and purposes, made of what we can see. This single graph is a declaration of independence from the dark matter model. The tension this creates is now immense and inescapable. If dark matter is a real, physical particle that clumps into halos around every galaxy, then how did these galaxies lose theirs? The gravitational slingshot idea, where a close encounter with another galaxy strips the dark matter away, seems less plausible when you have multiple examples. It would require a series of perfectly tuned cosmic accidents. Furthermore, if dark matter is so essential to galaxy formation that we built our entire cosmology upon it, how can entire galaxies form and survive without it? On the other hand, if the answer is a modification of gravity like MUND, which does not require dark matter, a different puzzle emerges. Why do the vast, overwhelming majority of galaxies perfectly mimic the behavior of having a dark matter halo? Why do their rotation curves stay so beautifully flat unless we invoke this invisible substance? A theory of modified gravity must explain why it works for some galaxies but seems unnecessary for others, a difficult balancing act. Each new dark matter-deficient galaxy, like a GC114905, is not just another entry in a catalogue. It is a piece of evidence in a cosmic courtroom drama. One side argues for an invisible, elusive particle we have never directly caught. The other argues that our fundamental law of gravity is subtly wrong on galactic scales. The falling rotation curve on that data plot is a silent, powerful testimony for the latter, a simple line that questions the invisible fabric of the universe itself. Our own solar system feels hauntingly quiet, a pristine wilderness untouched by any hand but our own. The silence here is a profound part of a larger cosmic mystery, the Fermi paradox. The universe is ancient, nearly 14 billion years old. Our galaxy alone contains hundreds of billions of stars, most with planets. If life and intelligence are common, the math suggests the galaxy should have been fully colonized, explored, or at least visited many times over by now. The galaxy should be buzzing with activity, yet when we look out and when we look around our own celestial backyard, we hear nothing and see no one. Our solar system shows no signs of extraterrestrial engineering, no ancient probes orbiting Saturn, no mining scars on asteroids, no beacon on the silent moon. The planets and moons we have explored with our robots and telescopes appear in a state of natural, untouched beauty, as if waiting for billions of years just for us to arrive. This pristine silence is itself an anomaly, One compelling explanation is the zoo hypothesis. It proposes that advanced civilizations are aware of us, but have chosen to place our solar system in a kind of galactic quarantine or nature preserve. They observe us without interference, allowing humanity to develop naturally, perhaps until we reach a certain level of maturity or technological sophistication. In this view, the silence is deliberate, a sign of respect or a strict ethical protocol. We are the exhibit, and the galaxy is the quiet, watching gallery. A more unsettling idea is the Great Filter. This theory suggests that there exists some nearly insurmountable barrier that prevents life from advancing to the stage of interstellar civilization. The haunting question is whether that filter is behind us. Perhaps the emergence of life itself was a one in a trillion fluke, or if it still lies ahead. Is the great silence because all civilizations, without exception, eventually discover a technology that destroys them or encounter a cosmic peril they cannot survive? Our solar system's quiet could then be a warning, a preview of a fate that awaits any species that reaches for the stars. Perhaps the most humbling possibility is that we are simply blind. An intelligence a million years more advanced than ours might use technologies that are completely undetectable to our current science. Their probes could be microscopic, their communications could use physics we have not yet discovered, or they might have transcended physical space entirely, living in simulated realities or higher dimensions. To them, our bustling solar system with its rockets and radio waves might look like the quaint, unnoticed stirrings of an anthill. Visualize a composite image. On one side, a serene, beautiful shot of Jupiter's swirling clouds or Saturn's rings, symbols of natural, untouched majesty. On the other, a vibrant artist's concept of a galactic core teeming with hypothetical megastructures, light trails, and activity. The contrast is stark. Are we alone in a vast, empty nursery, or are we the newest and quietest residents in a neighborhood so advanced we cannot even perceive our neighbors? The silence is not an answer. It is the universe's most persistent question. The pristine silence of our solar system speaks of a universe that feels untouched, but some stars scream their existence with a violence that defies all prediction. Among the most terrifying and brilliant objects in the cosmos are the luminous blue variables, stars so massive and unstable they exist on the very edge of self-destruction. The most famous is Eta Carinae, a binary star system over 7,000 light-years away that is a cosmic powder keg. In the 1840s, it staged an eruption so colossal it briefly became the second brightest star in the entire night sky, outshone only by Sirius. This was the Great Eruption, an event that released almost as much visible light as a true supernova, yet the star itself did not die. It survived, shrouding itself in a colossal cloud of its own expelled guts. The energy output was staggering, equivalent to a standard supernova, but the star's core remained intact. This is the central mystery. Our models of stellar evolution have no comfortable place for such a phenomenon. A star that massive, perhaps 120 times the mass of our Sun, should live fast and die young in a cataclysmic supernova or gamma-ray burst. It should not throw a titanic tantrum and then retreat, wounded but alive, behind a veil of dust. Historical drawings from the 1800s capture the awe of astronomers of the era, who watched a faint star suddenly blaze into prominence, a new beacon in the southern constellation of Carina. Modern observations, particularly from the Hubble Space Telescope, reveal the breathtaking aftermath. We see the Homunculus Nebula, a twin-lobed, peanut-shaped cloud of gas and dust expanding from the central star at millions of miles per hour. This nebula is not a gentle bubble. It is a shrapnel field from the explosion, glowing from within as it is illuminated by the ferocious light of the hidden stellar monster. The intricate, sculpted shapes suggest the eruption was not spherical, but highly directional, perhaps focused by the star's rotation or the influence of its companion. And that companion star is key to the puzzle. Eta Carinae is not alone. it orbits with another massive star in a highly elliptical 5.5-year dance. Many astronomers believe the Great Eruption was triggered by a critical interaction between the two. As the stars reached their closest approach, the gravitational pull of the companion may have severely distorted the primary star, tugging at its outer layers and pushing it past a point of stability. This could have triggered a massive release of energy, essentially causing the star to blow off its outer envelope without completely disrupting its core. The physics revolves around something called the Eddington limit. This is the maximum brightness a star can achieve before the outward pressure of its own radiation overcomes the inward pull of gravity. For a star as massive as Eta Carinae, it lives perpetually on this razor's edge. Any small perturbation, like the tidal pull from its companion, can cause it to exceed this limit, leading to massive outbursts and the ejection of whole solar masses of material. Yet, while the binary interaction provides a plausible trigger, the sheer scale and energy of the eruption still strain our models. The process is messy, involving complex hydrodynamics, radiation pressure, and stellar rotation in ways that supercomputers still struggle to simulate accurately. We are left with a celestial paradox, a star that performed a supernova's light show but refused the final curtain call. The homunculus nebula, beautiful and terrifying, is a monument to our incomplete understanding. It is the scar from a wound that should have been fatal, a reminder that the most massive stars in the universe can die in ways we have not yet written into the textbooks. The violent tantrums of stars like Eta Carinae forge new elements, scattering them into the cosmos. But the universe's original recipe, written in the first few minutes after the Big Bang, contains a glaring error in its instructions. This is the cosmic lithium problem, a fundamental mismatch between our theory of creation and the actual ingredients we find in the oldest stars. In the hot, dense furnace of the universe's first 3 to 20 minutes, a process known as Big Bang nucleosynthesis fused protons and neutrons into the lightest elements, hydrogen, helium, and trace amounts of lithium. Using our impeccable understanding of nuclear physics and the conditions of that primordial inferno, cosmologists can calculate with stunning precision how much of each element should have been made. For hydrogen and helium, the predictions match the observed abundances in the oldest, most pristine corners of space almost perfectly. It is a triumphant confirmation of the Big Bang theory. But for lithium-7, the calculations are off by a factor of about 3. The universe should contain roughly 3 times more lithium than we actually see when we look at the atmospheres of ancient stars. These stellar relics are our time capsules. Having formed from nearly pure primordial gas, their surface composition should mirror that of the early universe, preserving the Big Bang's chemical signature like a fossil. Yet spectroscopic analysis, which breaks their light into a rainbow to reveal the fingerprints of elements, consistently shows a lithium deficit. A graph of predicted versus observed abundances would show 2 bars for hydrogen and helium lining up in perfect agreement, while the bar for lithium-7 would show a theory bar standing tall next to a much shorter observation bar. This is not a small discrepancy. It is a direct contradiction at the foundation of cosmic chemistry. So where did all the lithium go? One line of investigation suggests our nuclear physics for that searing first few minutes might be incomplete. Perhaps unknown nuclear reactions occurred between those fleeting nuclei, destroying lithium-7 as fast as it formed. Or maybe the temperature and density of the early plasma varied in ways our simple models do not capture. Another possibility points the finger at the stars themselves. Could these ancient suns, over their billions of years of life, have somehow destroyed the lithium in their outer layers? Models of stellar interiors suggest processes like diffusion, where heavier elements sink inward, or mixing from turbulent currents could transport surface lithium down into hotter regions where it is fused into heavier elements. But to account for the uniform deficit we see across many different stars, this destruction mechanism would have to be remarkably efficient and universal. The most thrilling possibility is that this missing lithium is a clue to physics beyond the standard model. Certain proposed particles, like exotic types of dark matter or previously unknown forces, could have been active during those first minutes, altering the nuclear reaction rates and changing the final yield of elements. The lithium problem, therefore, is more than a bookkeeping error for astronomers. It is a potential crack in our understanding of the fundamental forces that govern the universe's first moments. The recipe for everything we see, from the stars to the planets to life itself, was written in that brief, explosive dawn. If we have mismeasured one of its core ingredients, we may have to revisit the entire cookbook of creation. While ancient stars hide a deficit of lithium, a modern experiment aboard the International Space Station has detected a puzzling excess of something else entirely. Mounted on the station's exterior, the Alpha Magnetic Spectrometer is a state-of-the-art particle detector, a 7.5-ton cosmic sieve that has been meticulously counting the subatomic rain from deep space for over a decade. Its data has revealed a strange overabundance in the cosmic rays showering Earth, an anomaly with thrilling implications. Among the countless protons and electrons, it found too many positrons. A positron is the antimatter counterpart of an electron, identical in mass but with a positive charge. When matter and antimatter meet, they annihilate in a flash of pure energy. Finding a significant number of these antimatter particles journeying across the galaxy is by itself unusual, but the real mystery is in the pattern. As the AMS measured cosmic rays at higher and higher energies, the fraction of positrons relative to electrons did something unexpected. It rose smoothly and steadily. If you look at the positron fraction graph, you see a clear, featureless upward curve beginning around 10 billion electron volts and continuing beyond 300 billion. This smooth rise is the heart of the puzzle. Conventional astrophysics can explain some positrons. We know that rapidly spinning neutron stars called pulsars act as natural particle accelerators, whipping charged particles to immense speeds. When these particles slam into surrounding gas, they can create pairs of electrons and positrons. The debris from these events should wash over us, contributing to the cosmic ray flux. But pulsar emissions are typically messy and clumpy. They should produce bumps and wiggles in the data, specific features tied to the energy output of individual known pulsars. The AMS graph shows none of that. It is a clean, relentless climb, as if the source is not a handful of stellar factories, but a vast, uniform sea of antimatter being generated across the galaxy. This smoothness is what makes scientists whisper one compelling possibility: dark matter. In many theoretical models, dark matter is not completely inert. When two dark matter particles collide in the dense halos around galaxies, they could annihilate each other, converting their mass directly into energy and producing a spray of standard particles, including electron-positron pairs. Because dark matter is thought to be spread in a vast, smooth halo around the Milky Way, its annihilation signal would be just that, smooth and featureless, exactly matching the AMS data. It would be an indirect glimpse of the universe's most elusive substance, not by seeing it, but by detecting the aftermath of its destruction. The hunt is now a fierce race to distinguish between this exotic explanation and more conventional ones. Could there be a population of unknown, very old pulsars whose combined signal appears smooth? Perhaps there are other astrophysical accelerators, like microquasars or supernova remnants, operating in ways we do not fully understand. Each new data point from the AMS tightens the constraints, narrowing the possible explanations. This is the cutting edge of cosmic detective work, parsing the subtle signals in a graph to decide if we are seeing the fingerprints of dying stars or the death throes of the universe's hidden mass. That steady, rising line on the positron fraction graph is more than data. It is a potential message written in antimatter waiting for its final translation. That steady rise of antimatter hints at invisible annihilations, but in September 2017, a single ghostly particle struck the Earth with a pinpoint address. Deep within the Antarctic ice, the Ice Cube Neutrino Observatory detected a neutrino with an energy of nearly 300 trillion electron volts. This was no ordinary subatomic whisper. It was a cosmic bullet, and for the first time in history, scientists could trace its path back to a specific source in the sky. Its origin was a monstrous engine 4 billion light-years away, a blazar known as TXS 0506+056. A blazar is the universe's most powerful particle accelerator. It is a galaxy centered on a ravenous supermassive black hole, but with a critical, terrifying alignment. This black hole is not sleeping. It is actively feeding, and it fires twin jets of plasma and radiation at nearly the speed of light. In the case of TXS 0506+056, one of those deadly beams is pointed directly at our solar system. We are staring straight down the barrel of a cosmic cannon. The detection triggered an unprecedented global hunt, a triumph of multi-messenger astronomy. The Ice Cube team issued an alert within minutes. Telescopes around the world and in space, from gamma-ray observatories like the Fermi satellite to optical and radio telescopes, swiveled to look at the coordinates. They saw the blazar in a state of extreme flaring, blazing with high-energy gamma rays. This was the smoking gun. The neutrino and the gamma-ray flare were products of the same catastrophic event. For decades, neutrinos had been cosmic mysteries. Trillions pass through your body every second, but they interact with matter so rarely they are called ghost particles. Catching one is difficult. Pinpointing where it came from was thought to be nearly impossible. This event changed everything. It proved that these elusive ghosts could be used as astronomical messengers, carrying information from the most violent environments that light alone cannot escape. The anomaly within this discovery is the sheer, incomprehensible energy of the neutrino itself. To accelerate a particle with no charge and almost no mass to such a velocity requires forces beyond anything we can create on Earth. The process must happen within the blazar's relativistic jet, a maelstrom of magnetic fields and shock waves near the black hole. Protons are likely accelerated to near light speed there, then collide with photons or other particles, creating a cascade that spawns both high-energy neutrinos and gamma rays. The neutrino that reached Ice Cube was a direct witness to that violence, a survivor from a zone of space-time twisted by gravity and magnetism into a natural particle collider of cosmic proportions. Visualize the data from that campaign. You would see the Ice Cube detector's grid in the Antarctic ice, with a single bright line marking the neutrino's incoming track. Overlay a map of the sky from the Fermi telescope, and a brilliant, flashing dot appears at the exact same coordinates, the flaring blazar. This convergence of signals, a ghost and a flash of light from the same distant cataclysm, marked the dawn of a new sense for humanity. We no longer just see the universe, we can now feel its most violent shudders through particles that travel unimpeded from the hearts of black holes. That ghostly neutrino was a messenger from a black hole's jet, but some of the universe's most profound messages are written not by particles but by bent light. Suspended in the deep field, a near-perfect circle of golden fire hangs against the dark. This is an Einstein ring, a cosmic mirage of staggering beauty and even greater consequence. The ring, catalogued as SPTSJ 041839-4751.8, is one of the most flawless examples ever seen. Its symmetry is so precise it looks like a piece of celestial jewelry, a halo forged by the warping of spacetime itself. The phenomenon is gravitational lensing, where the immense mass of a foreground galaxy cluster acts as a natural telescope, bending and magnifying the light from a far more distant galaxy directly behind it. When the alignment is exact, the light is smeared into a complete circle. While lensing is a confirmed prediction of Einstein's theory, This particular ring's perfection makes it an anomaly of a different kind, a laboratory so precise it has exposed a crack in our understanding of the cosmos's expansion. The ring is not just a pretty picture, it is a cosmic ruler and a clock, because we see the same distant galaxy in multiple, distorted positions around the ring. Astronomers can map the gravitational field of the foreground cluster with incredible accuracy. They can also measure the time delay, the tiny difference in how long it takes light to travel along each slightly different path around the lens. This delay, combined with the ring's size, allows for an independent, precise calculation of the distance to the background galaxy. And distance in an expanding universe is everything. It lets us measure the Hubble constant, the rate at which the universe is stretching apart. Here lies the profound tension. When scientists use pristine rings like this one, along with other cosmic ladders, they derive one specific value for the expansion rate. But when they use the afterglow of the Big Bang, the cosmic microwave background, they get a different, slightly slower value. This is not a small error bar. This is the Hubble tension, a discrepancy that has grown with each new, precise measurement. The universe seems to be expanding faster now than our best models of its infancy predict it should be. It is as if you carefully calculated how fast a rocket should be coasting based on its initial launch. But when you look out the window, it is clearly speeding ahead of your calculations. The stunning circular image from the Oumuamua telescope showing a fiery ring against the black is therefore a portrait of a crisis. That perfect circle is a geometric argument that something in our standard model of cosmology is missing. One compelling candidate is an unknown ingredient in the early universe, whimsically called early dark energy. This would be a transient form of energy that briefly surged during the cosmos's first few 100,000 years, giving expansion an extra kick that subtly changed the starting conditions for everything that followed. Another possibility is that dark energy itself, the force driving the accelerated expansion, is not constant as we assume, but has evolved over time. Or perhaps our understanding of gravity needs refinement on the largest scales. The Einstein ring does not solve the puzzle, but it sharpens it. Its flawless geometry provides one of the cleanest readings we have, and that reading stubbornly disagrees with another pristine set of data from the dawn of time. We are left with a universe that, when measured in two impeccable ways, gives two different answers. That golden ring in the void is more than a lens. It is a question mark written in starlight, asking us what fundamental piece of reality we have overlooked. Deep within the cosmic graveyard, a dead star refuses to be silent. Discovered in archival data from the Meerkat radio telescope in South Africa, the pulsar known as PSR J0901-4046 emits a radio beacon with a rhythm so slow it redefines what we thought was possible. Its pulse arrives not every millisecond, nor even every second, but once every 76 seconds. This is a heartbeat from a stellar corpse that should have ceased beating eons ago. To understand why this is so bizarre, picture a pulsar as a lighthouse. It is the rapidly spinning, magnetized core of a star that died in a supernova explosion. As it rotates, beams of radiation sweep across space like a cosmic searchlight. The faster it spins, the quicker the pulses. Most known pulsars complete a rotation in under 1 second, with many spinning hundreds of times per second. A 76-second period is not just slow, it is glacially, impossibly slow. It suggests a star that has spun down almost to a halt, losing its rotational energy over billions of years in a way our models cannot easily produce. The steady, deep thump of its pulse, rendered as sound, is a profound contrast to the frantic, buzzing chirps of its younger, faster cousins. You can hear it now, a deep, resonant beat against the silence, a metronome marking a time scale that feels almost geological. This slow rhythm points to two radical possibilities. First, it could be an incredibly ancient neutron star, one of the oldest ever detected. It has spun down so much that its magnetic field, which acts as a brake, must have decayed at an unusually slow rate, preserving a faint whisper of power for an unimaginable age. The second, more thrilling idea is that it belongs to a class of objects that has only existed in theory until now, an ultra-long period magnetar. A magnetar is a neutron star with an unimaginably powerful magnetic field, trillions of times stronger than Earth. Theorists have proposed that some magnetars could have such strong fields that they act as powerful brakes, slowing the star's spin to periods of many seconds or even minutes while still generating occasional bursts of radio waves. PSR J0901-4046 could be the first confirmed member of this hidden population, a missing link in the family tree of dead stars. Its discovery in so-called graveyard data adds another layer of irony. The observations that revealed it were not originally aimed at finding pulsars. They were buried in an archive, waiting for an algorithm and a curious scientist to sift through the noise and find this slow, steady signal. It forces us to reconsider the final stages of a pulsar's life. We thought we knew the timeline, from a rapid spin at birth to a gradual slowdown and eventual radio silence. This pulsar, with its patient 76-second tick, tells us the timeline is wrong. Perhaps the graveyard is not so quiet. Perhaps it is filled with the slow, deep heartbeats of stars we never thought to listen for, their long pauses between pulses hiding them in plain sight. What other rhythms, too slow for our expectations, are waiting to be heard in the static of the universe? The deep, slow heartbeat of a dead star measures time on a cosmic scale, but to understand the destiny of the entire universe, we must measure the fading light of stellar explosions across billions of years. This brings us to the dark energy anomaly, a subtle but terrifying whisper in the data that suggests the most dominant force in the cosmos might be changing its mind. Dark energy is the name we give to the mysterious pressure causing the universe's expansion to accelerate, a repulsive force that makes up about 70% of everything. For decades, the simplest assumption was that this force is constant, an immutable property of empty space itself, represented by a single number in Einstein's equations called the cosmological constant. This constancy leads to a specific, lonely fate for the cosmos, a gradual thinning into an eternal, cold, and empty darkness. But the light from ancient supernova is now hinting that this story may be wrong. The evidence comes from Type 1, a supernova, the cosmic standard candles. These are thermonuclear explosions of white dwarf stars that always reach about the same peak brightness. By measuring how bright they appear to us, astronomers can calculate their precise distance. By measuring how much their light has been stretched to redder wavelengths, they can determine how much the universe has expanded since the explosion. Plot these two pieces of information for thousands of supernovae across cosmic time, and you get a graph that charts the expansion history of the universe. The curve on that graph shows the expected gentle deceleration from early gravity, followed by the upward swing into acceleration driven by dark energy. But the latest, most precise data points are not landing perfectly on the smooth curve predicted by a constant dark energy. There are subtle deviations. The supernova from the universe's middle age, around 6 to 8 billion years ago, appear just a tiny bit fainter than they should be if dark energy's push has always been the same. This faintness suggests the expansion might have been speeding up slightly faster in the past than it is today. In other words, the strength of dark energy itself may be weakening over time. This is a seismic idea. If dark energy is not a constant but a dynamic field, often called quintessence, then the rules of the cosmos are still in flux. A graph of supernova distance versus redshift would show the elegant theoretical curve, but with a handful of critical data points from specific eras sitting just below the line, a quiet but systematic drift away from expectation. The implications rewrite our ultimate destiny. A constant dark energy leads to that cold, empty big freeze. But a dynamic dark energy that decays could, in a far future, fade away entirely, allowing gravity to potentially reassert its grip. This could lead to a big crunch, a reversal of expansion into a catastrophic collapse. Alternatively, if the field strengthened, it could lead to a big rip where the accelerating expansion becomes so violent it tears apart galaxies, stars, planets, and even atoms themselves in a final, catastrophic instant. The anomaly is exquisitely small, buried in the statistical uncertainties of measuring the light of explosions billions of light-years away. It could still be a systematic error, a subtle miscalibration of our cosmic rulers. But if it holds, it means the universe's dominant ingredient, the driver of its fate, is an active participant in its own story, not a fixed stage. We will be living not in a cosmos with a predetermined, quiet end, but in one that is still deciding how it will conclude, its final chapter being written by a force we are only now learning to see in the dim afterglow of dying stars. The fate of the cosmos may be uncertain, but one star's death was an act of sheer, unbridled defiance. In June 2015, the All-Sky Automated Survey for Supernova spotted a new point of light in a distant galaxy. Catalogued as a SASSN 15LH, this was not just another supernova. It was the single most powerful stellar explosion ever recorded by humanity, a detonation that redefined the limits of cosmic violence. At its blinding peak, it shone with the equivalent light of 570 billion suns, outshining its entire host galaxy and every other supernova in history by more than a factor of 2. For a brief moment, this single dying star produced more visible light than the combined output of every star in the Milky Way. The data from its light curve tells the story of impossible power. On a graph comparing brightness over time, a typical core collapse supernova from a massive star shows a sharp rise to a peak, followed by a steady, months-long decline powered by the radioactive decay of nickel and cobalt. The curve for a SASSN 15LH is a monster. Its peak is not just higher, it is in a different league entirely, a towering spike that dwarfs every other line on the chart. Then, just as curiously, its decline showed strange rebrightenings, as if the engine of destruction kept sputtering back to life. The first assumption was that this must be a superluminous supernova, a rare class thought to be powered by the collapse of a star into a magnetar, a rapidly spinning, highly magnetized neutron star. The incredible spin and magnetic field would inject enormous energy into the expanding debris, creating a super bright blast, but a critical detail refused to fit. Superluminous supernova almost always occur in small, dwarf galaxies that are actively forming stars, places rich in the pristine, massive stars that can produce such exotic explosions. The host galaxy of a SASSN 15LH was the opposite, a massive, red and passive elliptical galaxy, a quiet retirement community for old stars. It was the last place anyone would expect to find a young, monstrous star dying in this way. This mismatch of location and event forced a radical rethink. The leading theory now is that we did not witness a supernova at all, but something even rarer and more violent, a tidal disruption event pushed to its absolute extreme. In this scenario, a wandering star ventured too close to the supermassive black hole at the galaxy's center. But this was no ordinary black hole. Theorists propose it is a rapidly spinning monster, a Kerr black hole. The star would not just be torn apart by tides, it would be shredded into a stream of gas that then collides with itself as it swirls into the accretion disk. The resulting friction and shocks could release a staggering amount of energy, far surpassing a normal tidal disruption event and mimicking the light output of a supernova. It would be a black hole having a star for a snack and burping out a fireball of cosmic proportions. The challenge with a SASSN 15LH is that it sits at the boundary of our categories. Our charts and classifications are built from the typical and the repeated. When we encounter a one-off event of such staggering extremity, it exposes the limits of our vocabulary. Was it a supernova or a tidal disruption? The light curve alone cannot give a definitive answer because we have nothing to compare it to. It is an outlier so far from the norm that it forces us to invent new physics or combine existing ideas in ways we never considered. This single point of light, now faded, leaves behind a profound lesson. The universe's most violent acts may not follow the scripts we have written for them, and the brightest beacon in the dark can sometimes be the hardest to understand. The universe's most violent explosions rewrite the rules of physics, but our cosmic inventory holds a quieter, more fundamental error in its accounting. According to the precise recipe of the Big Bang, a specific amount of normal matter, the protons and neutrons that make up stars, planets, and us, should exist today. This is the predicted budget of baryonic matter, yet when astronomers tally everything they can see, all the stars in all the galaxies, all the glowing gas clouds, all the dust, they come up embarrassingly short. Over half of all the normal matter in the universe is simply missing. It is not dark matter, which is a separate, mysterious substance. This is the regular atomic stuff we are made of, and it has vanished from the cosmic ledger. Imagine if you carefully counted all the money in your wallet, your bank account, and your pockets, only to find you had less than half of what your pay stub clearly stated you earned. The universe has a similar, profound accounting error. We are left searching for the universe's hidden savings, the missing baryons. The leading suspect is not a single, massive object, but a vast, diffuse fog. Theorists believe the missing matter exists as a superheated gas, a plasma with temperatures ranging from hundreds of thousands to millions of degrees, strung along the invisible filaments of the cosmic web. This is the warm-hot intergalactic medium, or WIM. It is the universe's hidden plumbing, the gaseous highways connecting the dense galaxy clusters like sparkling cities. The problem is that this gas is so hot and so thin it is almost invisible. It does not glow brightly in visible light, and its extreme temperature means it emits only very specific, faint wavelengths of ultraviolet and X-ray light that are notoriously difficult to detect from within our atmosphere-obscured planet. For decades, the WIM was a ghost, a theoretical necessity that eluded all direct observation. A schematic of the cosmic web would show the brilliant knots of galaxy clusters connected by faint, glowing threads, a luminous neural network of hot gas spanning the emptiness. The breakthrough in this cosmic detective story came from using the universe's most brilliant and fleeting flashes as probes, fast radio bursts. These mysterious millisecond bursts of radio energy, originating from galaxies billions of light years away, travel across the cosmos to reach us. As they journey through space, they interact with every electron in their path. Each electron causes a tiny, frequency-dependent delay in the burst's arrival time, an effect called dispersion. By measuring this dispersion with incredible precision, astronomers can essentially count the total number of free electrons the burst encountered on its multi-billion, light-year journey. This measurement acts as a cosmic scale, weighing all the ionized gas, including the elusive WIM, that lies between the burst and Earth. When researchers analyzed a single burst from a distant galaxy, they used this method to derive the total amount of normal matter in the intergalactic medium. The number they found finally matched the Big Bang's prediction. The missing baryons had been found not in shining galaxies, but in the searing, invisible fog between them. This discovery transforms our picture of the cosmos. The universe is not mostly empty space between islands of matter. It is filled with a tenuous, hot ocean, a plasma that contains more normal matter than all the stars and galaxies combined. We live in a universe where the most familiar form of substance is not in the shining points of light, but in the faint, hot breath that fills the voids. Finding it required not a bigger telescope, but a cleverer kind of measurement, using the briefest cosmic signals to illuminate the darkest corners of existence. If the whim is the hidden ocean, then what other unseen currents might be flowing through the spaces we once thought were empty? Far beyond Neptune's orbit, in the deep freeze of our solar system's frontier, a handful of icy wanderers are moving as if pulled by a ghost. These are the trans-Neptunian objects, the frozen remnants of the solar system's formation, and their orbits tell a story of a hidden architect. The most famous of these, the dwarf planet Sedna, follows a lonely, looping path that takes 12,000 years to complete, swinging from a distant, cold aphelion far beyond the Kuiper belt to a slightly closer perihelion, yet never coming near the giant planets. Its orbit is not just elongated, it is inexplicably tilted. Sedna is not alone. Several other extreme objects share this peculiar signature, their orbits clustered in space, their points of closest approach to the Sun oddly aligned. This gravitational herding is the primary evidence for a hidden giant, a hypothetical planet 9. The mathematics is compelling. To shepherd these distant bodies into such a specific, clustered configuration requires the steady, persistent tug of something massive, perhaps 5 to 10 times the mass of Earth, orbiting on a highly elliptical path thousands of times farther from the Sun than we are. An animation of this scenario is mesmerizing. You would see the familiar orbits of the 8 known planets as tight, near circular rings close to the Sun. Then, far beyond, a sparse spray of dots representing the icy objects, their long, elliptical orbits all pointing in a similar direction, their arguments of perihelion mysteriously group. Overlaying this in a contrasting color would be the proposed monstrously wide orbit of Planet 9 itself, a slow, grand ellipse taking perhaps 20,000 years to complete, its gravitational influence sculpting the chaos over eons. Finding this phantom world, however, is a monumental challenge. Its proposed orbit is so vast that it could be almost anywhere along that gigantic ellipse. It would reflect virtually no sunlight, making it a faint, cold speck against an already black sky. Telescopes like Subaru on Mauna Kea are engaged in a painstaking, needle-in-a-haystack search, scanning slivers of the predicted orbital path for a moving dot of light. Yet, as with all profound anomalies, alternative explanations exist. Could the orbital clustering be an observational bias, a trick of where we have pointed our telescopes? Possibly, though subsequent discoveries have strengthened the signal. Another intriguing idea is that the collective gravity of many smaller, unseen objects in the outer disk could produce a similar shepherding effect without a single large planet. This would be a gravitational whisper from a crowd rather than a shout from a king. This modern mystery beautifully echoes history. In the 1840s, irregularities in the orbit of Uranus led mathematicians Urbain Le Verrier and John Couch Adams to predict the existence and position of Neptune, which was then found exactly where their calculations said it would be. Today, the anomalous orbits of Sedna and its kin are the new irregularities, the wobbles in the clockwork of our solar system that point to an unseen hand. Whether the culprit is a true Planet 9, a swarm of smaller bodies, or something else entirely, the lesson is the same. Our cosmic backyard, which we thought we had mapped and understood, still holds profound secrets in its darkest, coldest reaches. The hunt for this hidden world is more than a search for a new planet. It is a test of our understanding of gravity itself at the very edge of our home system. The hunt for hidden worlds often leads us outward, but some of the most shocking discoveries wait in the places we thought we knew best. Even Mercury, the sun-scorched innermost planet, holds a secret that defies its own identity. Data from NASA, a messenger probe which orbited the planet from 2011 to 2015, delivered an unequivocal and startling confirmation. Deep within the permanently shadowed floors of craters at Mercury's north and south poles, there are vast deposits of water ice. This is a profound cosmic contradiction. By day, surface temperatures on Mercury can soar to 800 degrees Fahrenheit, hot enough to melt lead. Yet, in these specific, frigid sanctuaries of eternal night, the thermometer plummets to nearly 400 degrees below zero. The ice survives not in spite of the sun, but because of the planet's peculiar geometry. Mercury has virtually no axial tilt, meaning its rotational pole points almost straight up and down relative to its orbit. This creates depressions near the poles like deep craters, whose rims cast shadows that never see sunlight. Within these sunless pits, known as cold traps, any volatile material that finds its way in is locked in a deep freeze for eternity. The evidence came from multiple instruments. Earth-based radar had long hinted at strangely bright, reflective patches at the poles. Messenger neutron spectrometer then detected the telltale signature of hydrogen, a key component of water, concentrated in those exact same locations. Finally, images from the probe's cameras captured the stark visual proof. They show sun-drenched, scorched plains of gray cratered rock. But when the data is overlaid, those permanently shadowed regions light up in false color, revealing brilliant white deposits hiding in the abyssal dark. The central question becomes, how did water, one of the most fragile of compounds, arrive on a planet that is practically inside a furnace? The leading explanation is a delivery service that has operated for billions of years. Comets and water-rich asteroids wandering through the inner solar system have periodically slammed into Mercury's surface. These violent impacts vaporize their water content, sending a temporary atmosphere of steam billowing across the planet. Most of this vapor is quickly lost to space or broken apart by solar radiation, but a fortunate fraction of those water molecules will hop and bounce across the landscape in a random walk. If even a single molecule manages to bounce into one of the deep polar cold traps, it is captured forever, adding to a glacier that grows one molecule at a time over eons. It is a process of accumulation by improbable survival. The ice we see today is not a remnant of a wet, ancient Mercury. It is an archaeological record of countless cosmic deliveries, a library of impacts written in frozen water and preserved in the only vaults cold enough to keep it. This discovery reshapes our understanding of not just Mercury, but of the entire solar system's economy. If water can be shipped and stored on the planet closest to the sun, then no world is truly dry. It reveals that the ingredients for life are not just scattered randomly, but can be strategically deposited and preserved in the most unlikely of bank vaults, waiting in the eternal shadows for a future we have only begun to imagine. From the frozen vaults of Mercury, we leap across the cosmos to a signal that beats with the regularity of a cosmic metronome. In a distant galaxy 500 million light-years away, a source catalogued as FRB 180916.J0158+65 does something no other cosmic phenomenon had done before. It repeats, and it does so on a perfect schedule. This fast radio burst repeater fires off its brilliant millisecond flashes in a cycle of 16.35 days. For roughly 4 days, it is active, capable of unleashing multiple bursts. Then, for the next 12 days, it falls completely silent. This precise periodicity is a gift and a profound constraint, a clue etched into the fabric of time itself that tells us we are not witnessing random detonations, but a clockwork mechanism. A timeline of its emissions reveals the pattern with stunning clarity. Imagine a horizontal line representing time marked off in 16-day intervals. Above that line, a series of vertical spikes appears only within a distinct, repeating 4-day window followed by a clean, empty gap. This is not noise. This is a signature. Such a clean, predictable cycle immediately points to an orbital dance. The leading explanation is that the object producing the bursts, likely a highly magnetized neutron star called a magnetar, is locked in a binary system with a massive companion, perhaps another star or a black hole. As it orbits, its environment changes dramatically. For those 4 days of activity, the magnetar is passing through a region of space filled with dense plasma, perhaps a stellar wind or a debris disk from its companion. When the magnetar's powerful magnetic field interacts with this thick soup of charged particles, it can trigger the cataclysmic events that generate the fast radio bursts. Then, as it moves along its orbit into a cleaner, emptier region of space, the engine is effectively switched off and the 12 days of silence begin. This model transforms the mystery from a what to a where. We are no longer just hunting for a source, we are mapping its celestial neighborhood. The 16-day period tells us the orbital separation, the masses involved, and the nature of the environment that acts as both a trigger and a shutter. It rules out explanations involving isolated, one-off cataclysms like a single star collapsing or merging. This repeater is a system, a relationship, and its rhythmic outbursts are a direct readout of its orbital mechanics. By studying the precise properties of the bursts during the active window, scientists can probe the density and magnetic fields of the plasma it is moving through, turning this distant object into a unique natural laboratory. The pattern is a key, but the lock it opens is for all fast radio bursts. If this one's rhythm is due to an orbit, could other, non-repeating bursts be from similar systems where we just see a single flash from a particular orbital point? Or are they truly singular events? The predictable heartbeat of FRB 180916 is a Rosetta Stone, beginning to translate the violent, cryptic language of these cosmic flashes into the orderly grammar of orbits and interactions. It suggests that even the most violent and fleeting signals in the universe can be born from something as simple and elegant as one object circling another in the dark. The rhythmic heartbeat of a distant fast radio burst reveals a universe governed by predictable orbits, but the ghostly galaxies we are about to meet follow no such predictable rule. The case of the dark matter-deficient galaxies has grown from a curious exception into a full-blown crisis with the discovery of a third, and then a fourth member of this impossible family. Galaxies like a GC 242019, a faint, wispy system drifting in solitude, now join the earlier examples to form a small but undeniable class of cosmic outliers. They are not alone anymore. Each new detection, each faint smudge of starlight confirmed to spin without the invisible anchor of dark matter, deepens the mystery and tightens the vise around our most cherished cosmological model. The initial hope was that these were tragic flukes, galaxies violently robbed of their dark matter. The theory was elegant. If a small galaxy ventured too close to a massive neighbor, the brutal gravitational tides could rip away its diffused dark matter halo while leaving the more compact cluster of stars relatively intact. It would be a form of cosmic theft, leaving behind a stellar skeleton. This explanation could work for a galaxy found near a giant cluster, but the new candidates, like a GC 242019, are often found in quiet, isolated neighborhoods of space. They are cosmic hermits with no massive galaxy nearby that could have performed such a surgical gravitational stripping. Their loneliness makes the theft theory implausible. They appear to have formed, or at least persisted for billions of years, without ever possessing a significant dark matter halo to begin with. This isolation is a silent scream that the problem is fundamental. The dilemma this poses for the lambda CDM model, the foundation of modern cosmology, could not be more profound. Lambda stands for dark energy, CDM for cold dark matter. This model has been spectacularly successful at explaining the large-scale structure of the universe, the patterns in the cosmic microwave background, and the very fact that galaxies exist at all. Its central pillar is that dark matter halos form first, and their gravity acts as a seed to gather the normal gas that eventually cools and forms stars. In this story, a galaxy without dark matter is not just unlikely, it is a logical impossibility. It is like finding a sandcastle built without any sand, just the shape of the bucket hovering in mid-air. The existence of multiple such galaxies forces a brutal choice. Either our method for detecting dark matter in these systems is somehow flawed, a possibility scientists are rigorously checking, or the lambda CDM model is missing a crucial piece of physics that allows for a rare but real pathway to form galaxies from stars and gas alone. A gallery of these objects tells the story visually. They are not majestic spirals or glowing ellipticals. They are ultra-diffuse ghosts, faint smears of light so transparent you can see distant galaxies shining right through them. In composite images, their ethereal forms are often circled or highlighted, appearing as pale, fuzzy patches against a rich starfield. Their very appearance, wispy and insubstantial, seems to mirror their gravitational deficit. They look like what they are, collections of stars barely holding themselves together. This growing collection of faint anomalies has turned a quiet corner of astronomy into one of the most heated debates in science today. It is a debate that cuts to the core of what we think the universe is made of and how it built the structures we see. Are we on the verge of discovering a new, unexpected mode of galaxy formation? Or are these cosmic ghosts pointing us toward a revolution in our understanding of gravity itself? The answer is written in the faint light of these impossible islands, and every new one we find adds another sentence to a story we are only beginning to read. The faint ghosts of galaxies challenge our understanding of gravity on the largest scales, but a pair of human-made probes once presented a tiny, stubborn mystery much closer to home. The Pioneer 10 and 11 spacecraft, launched in the early 1970s to explore the outer planets, became unintended experiments in fundamental physics long after their primary missions ended. As they coasted into the deep freeze beyond Pluto, tracking their radio signals revealed something deeply unsettling. Both spacecraft were slowing down. Not from the sun's gravity, which was pulling them back, but by an amount ever so slightly greater than our equations predicted. It was a minuscule, anomalous sunward acceleration, just 10 billion times weaker than the gravity we feel on Earth, but it was there and it was persistent. For decades, this pioneer anomaly haunted physicists. Here was a deviation from Newton and Einstein's laws, measured not in some distant galaxy, but in the trajectories of our own robotic envoys. It was a whisper that our grasp of gravity might be flawed, even here in our own celestial backyard. A diagram of their trajectories tells the story. You see the graceful arcs past Jupiter and Saturn, then the long, lonely paths out of the solar system. But the data plots show the actual distance of the pioneers creeping just below the predicted line, as if an invisible hand was ever so gently applying a brake. This tiny discrepancy fueled intense speculation. Could it be evidence for modified gravity, a hint of the same physics that might explain galaxy rotation without dark matter? Perhaps it was a sign of unseen matter in the outer solar system, or even a subtle effect of the universe's expansion acting on small scales. The mystery endured for over 30 years, a testament to how the most precise measurements can reveal gaps in our knowledge. The resolution, when it finally came, was a masterpiece of scientific detective work and a profound lesson in humility. A team of researchers undertook a monumental effort, recovering decades-old engineering data and building a supremely detailed thermal model of the aging spacecraft. They realized the answer was not in the fabric of space-time, but in the craft's own plumbing. The pioneers were powered by radioactive thermoelectric generators. These units produced heat which the spacecraft radiated into space to stay warm. The critical insight was that this radiation was not perfectly symmetrical. More heat was emitted from the rear of the craft, where the power units were mounted, than from the front. This anisotropic thermal radiation created a tiny but measurable photon thrust, a gentle push of light itself acting as a brake. When this painstakingly calculated thermal recoil force was added to the equations, the anomalous acceleration vanished. The mystery was solved not by new physics, but by old-fashioned engineering and relentless attention to detail. The Pioneer anomaly stands as one of science's great cautionary tales. It reminds us that before invoking revolutionary concepts like modified gravity or hidden dimensions, we must first exhaust every mundane possibility, no matter how complex. It is a tribute to Occam's razor, the principle that the simplest explanation is often correct, even when finding that simplicity requires years of excruciating work. Those two silent probes, now drifting in the interstellar dark, taught us that the universe's greatest secrets can sometimes be hidden in the warmth of a machine we built ourselves. The thin, cold air of Mars is breathing in a rhythm we do not understand. For over 3 Martian years, the Curiosity rover's sample analysis at Mars Instrument has been sniffing the atmosphere inside Gale crater, and it has recorded a gas behaving in a way that defies all logic. The level of molecular oxygen, the same gas we breathe, does not follow the predictable seasonal pattern set by other atmospheric gases like nitrogen or argon. Instead, it spikes and plummets erratically, rising by up to 30% in the spring and summer before crashing back to predicted levels in the fall. A graph of this data is a portrait of atmospheric chaos. The lines for other gases trace smooth, repeating waves over the Martian years, but the oxygen line is a frantic scribble, a jagged, unpredictable climb and fall that overlaps the other curves like a frantic heartbeat. This is not a measurement error. It is a persistent, reproducible anomaly that our best chemical models of the Martian atmosphere cannot begin to reproduce. Something on Mars is actively producing and then destroying large quantities of oxygen, and we have no idea what it is. This mystery deepens when paired with Curiosity's other great atmospheric puzzle, the sporadic methane spikes. Both gases, potential biomarkers on Earth, are appearing and disappearing in the Martian air in ways that suggest active, hidden sources and sinks. The oxygen behavior is particularly baffling because it is so seasonal. The increase suggests a source that turns on with warmth or sunlight. One leading hypothesis points to the chemistry of the Martian soil. The regolith is rich in perchlorates, salts that can break down when heated, potentially releasing oxygen. But laboratory experiments show this process is far too slow to account for the sheer volume and speed of the observed changes. Could there be a catalytic process involving ultraviolet light and mineral surfaces that we have not yet replicated? Another line of thought dips below the surface. If briny, liquid water exists in shallow aquifers, complex chemical interactions between the water, subsurface rocks, and perhaps even microbial life could produce oxygen that slowly seeps into the atmosphere. Yet any geological or biological explanation must also account for the gas's rapid disappearance. What powerful chemical destroyer is waiting to scrub the oxygen from the air as temperatures drop? The data forces us to admit a humbling truth. Our understanding of Martian atmospheric chemistry is a rough sketch, missing entire chapters of active processes. The planet is not a dead, static world. Its soil and atmosphere are engaged in a complex, cryptic exchange, a conversation written in gases we are only just learning to measure. Every unexpected spike on that graph is a question, a clue that Mars, even in its apparent stillness, is a world of hidden activity. What other secrets is its thin, whispering wind waiting to reveal? The thin air of Mars whispers of hidden chemistry, but in the silent fabric of spacetime itself, a collision once rang out that broke the rules of stellar life and death. On May 21, 2019, the twin detectors of LIGO and the Virgo Observatory felt a tremor in the cosmos. It was the gravitational wave signal designated GW1-90521, the shudder from 2 black holes spiraling together in a catastrophic dance over 7 billion light-years away. The data revealed a merger of staggering scale, creating a final black hole with a mass of 142 times that of our Sun. That number is not just large. It is forbidden. This new black hole landed squarely in what astrophysicists call the pair instability mass gap. According to our most robust models of how the most massive stars die, black holes should not be able to form in this specific weight class between roughly 65 and 120 solar masses. The theory is precise. When a star with a core between those masses reaches the end of its life, the heat in its core becomes so intense that it starts spontaneously converting energy into pairs of electrons and positrons. This process robs the core of the thermal pressure supporting it against its own immense gravity. The result is not a gentle collapse, but a runaway thermonuclear explosion so violent it completely obliterates the star, leaving behind no black hole at all, just a cloud of scattered elements. It is a cosmic dead zone for black hole formation. So how did two black holes, each massive enough to be on the edge of this gap, find each other and merge? The first possibility is as thrilling as it is logical. The parents of this final monster were not born from collapsing stars, they were born from violence themselves. They could be second-generation black holes, the remnants of earlier mergers in a dense stellar environment like a globular cluster. In this scenario, two smaller black holes, each formed from a star, would merge. Their product would then wander through the cluster until it found another partner, leading to a second merger. This hierarchical build-up could easily skip over the forbidden mass gap entirely, creating a black hole that no single star could ever produce. It is a cosmic legacy, a dark heir built from the graves of its predecessors. The second possibility is more humbling. It forces us to question our understanding of the final moments of the most massive stars. Perhaps our models of supernova physics, of stellar winds, or of the internal mixing within these giant suns are incomplete. Maybe stars can, under rare conditions, hold themselves together just enough to collapse directly into this forbidden mass range without triggering total disintegration. Or perhaps the black holes were enveloped in thick disks of gas that altered their evolution in ways we are only beginning to model. This single event, a blip in data that lasted less than 1/10 of a second, challenged a fundamental pillar of astrophysics. It did more than that. It opened a new window onto the hidden population of black holes in the universe. Before gravitational wave astronomy, we could only infer the existence of black holes through their effects on light. Now we can listen to them form. The sound of GW190521 is a low, deep chirp, a bass note that rises in frequency and amplitude before cutting off abruptly at the moment of merger. It is the sound of two impossibilities finding each other in the dark. That brief signal tells us the cosmic graveyard contains residents we never thought could exist, and that the stories written by gravity are far stranger than the stories we have written for the stars. From black holes that break mass limits to Martian air that breathes unpredictably, we have crossed a universe of profound and beautiful contradictions. We have witnessed 35 cosmic head-scratchers, from the galactic scale pull of the Great Attractor to the solar system quirk of Mercury's hidden ice. Each one stands as a monument not to a failure of science, but to its essential, thrilling purpose. These anomalies are not errors in the data, they are guideposts. They are the universe's way of tapping us on the shoulder and pointing toward the next chapter in the story of everything. A galaxy without dark matter is not a mistake. It is a clue screaming that our model of cosmic structure is incomplete. The eerie silence of the Fermi paradox is not an answer. It is a profound question about life's place in the cosmos. The steady heartbeat of a 76-second pulsar and the smooth rise of antimatter from the void are not glitches. They are messages in a code we are still learning to crack. This journey forces a necessary humility. We have mapped the heavens and peered back to the first light, yet with every new telescope and every deeper look, the cosmos reveals another layer of mystery, another rule it delights in breaking. This is not cause for despair. It is the source of our greatest excitement. Every unexplained signal, every impossible orbit, every chemical surprise on a distant world is an invitation. An invitation to think bigger, to question deeper, and to build the next generation of tools that will turn today's baffling anomaly into tomorrow's foundational truth. So what comes next? The story is still being written. The James Webb Space Telescope is peering at those impossibly mature infant galaxies. New gravitational wave detectors are listening for more forbidden black hole mergers. Probes are sniffing the atmospheres of distant exoplanets. The hunt for Planet 9 continues in the frozen dark. This is your front row seat to the greatest detective story of all time. Stay curious. On a clear night, step outside and look up. That starry expanse is not a static painting. It is a living, breathing, and deeply weird puzzle, and we are all pieces of it. Which of these 35 cosmic glitches reshaped your view of reality the most? Let us know in the comments below. And if you want to join us for the next deep dive into the wonders and mysteries of the cosmos, be sure to subscribe. The universe still has countless secrets left to tell.